I now call to order the lecture portion of the Society's 2513th meeting in what is now the 154th year since its founding on March 13th, 1871. Good evening, everyone. My name is Larry Milstein. I am president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members, guests, and friends to tonight's PSW lecture by Joshua Semeter. The Society is grateful to PSW Full Year Series sponsors, PSW member Mike Helton and Helton Associates LLC. Thank you, Mike. To our Spring Series sponsor, PSW member Joe Schulman. Thank you, Joe. And to the sponsor of tonight's lecture, PSW member Michael Sandifer. Thank you, Michael. The Society, needless to say, needs your support to meet its expenses for the year. So if you have not given or feel you can give more than you already have, please don't hesitate to donate. You may see me about how to do that, but generally speaking, you could do it through the web. If you're interested in sponsoring a lecture, please let me know or send us an email. I'm pleased to announce the following new members. A.M. Paulos and all right. An electrical engineer interested in astronomy, electromagnetics, and RF propagation, who learned at PSW from PSW members Rebecca Prather and Stephanie Smiley. Thank you, Rebecca and Stephanie. Julia Kaywood, a student interested in a frequent attendee of our lectures, by the way, and dinners. A student interested in geology, paleontology, especially dinosaurs, archaeology, and astronomy. We learned up PSW from PSW member Matt Kaywood, her dad. Thank you, Matt. And Safi Bakal, a physicist and author interested in physics, astronomy, and biology, who learned at PSW from an event at the Cosmos Club. Welcome, Safi. And tonight's speaker, Joshua Semeter, who learned of PSW from our invitation to him to speak here tonight, and whose interests will sort of be clear in part from tonight's lecture. Please join me in welcoming them all to membership. All members are entitled to a signed copy of Volume 17 of the Bulletin of the Philosophical Society of Washington. If you've not received yours, please see me after the meeting. It used to be Volume 1, but now it's Volume 17, because Volume 17 has most of the formative information from Volume 1 and a whole bunch of other interesting stuff, including histories of the Society and minutes of early meetings and lists of our Henry speakers and things like that. If you're interested in membership, you can access a membership application on the PSW website by clicking on the blue Join button at the upper right-hand corner of the home page. If you're here in the Powell Auditorium, you can access the application using the QR code on the business cards that are distributed on the table at the back of the room. All who are genuinely interested in science are welcome to join PSW. And with that, Recording Secretary Scott Matthews will now present the minutes of the 2512th meeting and the lecture by David Bennett on detecting exoplanets by gravitational microlensing. Scott.
Thank you, Larry. Good evening. On March 21st, 2025, members of the Society and guests joined the speaker for a reception and dinner at 5:45 p.m. in the members' dining room at the Cosmos Club. Thereafter, they joined the other attendees in the Powell Auditorium for the lecture proceedings. In the Powell Auditorium of the Cosmos Club in Washington, D.C., President Larry Milstein called the lecture portion of the 2512th meeting of the Society to order at 8:02 p.m. Eastern Time. He began by welcoming attendees, thanking sponsors for their support, announcing new members, and inviting guests to join the Society. Scott Matthews then read the minutes of the previous meeting, which included the lecture by Joanna Drucker titled Alphabet Histories, The Origin of Letters from Antiquity to the Present. The minutes were approved pending a minor correction. President Milstein then introduced the speaker for the evening, David Bennett of the Goddard Space Flight Center. His lecture was titled Depicting Exoplanets by Gravitational Microlensing, Surveys, Gaps, and Rogues. The speaker began by saying that although humans have been discussing the possibility of life on other planets since the time of the ancient Greeks, the real story of exoplanets began in 1995 with the discovery of the first two planets outside our solar system. He then discussed the habitable zone, the range of orbital distances over which a planet is likely to have liquid water. Bennett discussed the physics of planet formation, claiming that the models were too complex for first principles calculations and required a number of approximations and guesses. He said, quote, exoplanet theory makes no grand predictions, and progress comes from observation, end quote. The speaker then discussed the methods for detecting exoplanets. These included ground-based and space-based imaging, astrometry, Doppler radar velocity, transits, and gravitational microlensing. He showed an animation depicting reflex motion, the change in the position and velocity of a host star due to an orbiting planet. He discussed how Doppler radial velocity and astrometry measurements could reveal this reflex motion. Bennett indicated that the majority of the first 500 exoplanets discovered were found by radial velocity measurements. He described the transit method, wherein an apparent brightness of the host star is reduced as the planet passes in front of the star, noting that the majority of recently discovered exoplanets were found using this method and the Kepler Space Telescope. Bennett then discussed gravitational lensing, the prediction of Einstein's theory of general relativity that light propagating in a gravitational field will appear to bend due to the curvature of space-time. He listed several of the seminal papers on the subject, including Einstein's 1936 paper on the, quote, lens-like action of gravitational fields, Paczynski's 1986 paper on the search for dark matter, Mao and Paczynski's 1991 paper on the search for planetary systems, Alcock's 1993 paper on the observation of microlensing in the Large Magellanic Cloud, and the 1996 paper by the speaker and his late wife, Sun Hong Rhee, on the detection of Earth-mass planets by gravitational microlensing. Bennett described the physics of planetary microlensing. As a lens star, or host star, transits in front of the source star, the gravitational field of the lens star causes the light from the source star to bend in such a way that the source star appears larger. This magnification, which is initially small, increases to a maximum value and subsequently decreases as the lens star passes in front of the source star. This smooth increase and subsequent decrease in the apparent size of the source star can be interrupted by sharp spikes in the magnification if a planet is present. These spikes in the magnification, as a function of time, constitute the observation of an exoplanet by gravitational microlensing. The speaker indicated that the probability of finding a source star and a lens star in the right position, as observed from Earth, was quite small, on the order of a few parts in 10 to the 6. He said that the galactic bulge towards the center of the Milky Way was the best place to look for planetary companions. He then discussed some of the results from recent microlensing surveys, including the MOA2, which found 30 exoplanets between 2005 and 2012, and the KMT-NET survey, which found 63 exoplanets during its 6 years of operation. He discussed how these results compared to various models of planet formation, or core accretion models. Bennett showed animations and hydrodynamic simulations of gas accretion during the early phases of planet formation. The speaker ended his talk by describing the types of observations expected to be performed with the Nancy Grace Roman Space Telescope, scheduled to be launched in 2026. The search for exoplanets is one of the primary objectives of this mission. This instrument will have significantly higher resolution and significantly faster survey times than current ground-based observatories. The lecture was followed by a question and answer session. A member asked if our current observational techniques would allow detection of non-planetary features around other stars, particularly asteroids or asteroid belts. Bennett responded that we have not been able to make such measurements with ground-based systems, and that there was some discussion as to whether the Roman Space Telescope would be capable of such observations. A member noted that some researchers have claimed that the distribution of planets in our solar system is logarithmic and is related to Boyle's law. He asked if such logarithmic distributions have been observed in other systems. Bennett responded that Boyle's law is, quote, partly an accident, saying that the law does not appear to be true in general, but that there may be planet formation mechanisms that make such a distribution more likely. A guest on the live stream asked whether you could detect exoplanets using gravitational waves, and can you use microlensing with gravity waves as opposed to light? Bennett responded, no, saying the gravitational fields of the planets are quite small. After the question and answer period, President Milstein thanked the speaker and presented him with a PSW rosette, a signed copy of the announcement of his talk, and a signed copy of Volume 17 of the PSW Bulletin. He then announced speakers of upcoming lectures and made a number of housekeeping announcements. He adjourned the 2512th meeting of the Society at 9:57 p.m. Eastern Time. Temperature in Washington, D.C., 12.8 degrees Celsius. Weather, mostly cloudy. Audience in the Powell Auditorium, 44. Viewers on the live stream, 26, for a total of 70 live viewers. Views of the video in the first 2 weeks, 419. Respectfully submitted, Scott Matthews, Recording Secretary.
Well, thank you, Scott, very much for distilling what was a very technical talk and getting all of the main points, I think. Really great job. The minutes are accepted as read, subject to the one correction, and will be posted to the website in due course. And we now turn to tonight's lecture by Joshua Semeter. Josh is professor of electrical and computer engineering and director of the Boston University Center for Space Physics. He was a member of the NASA UAP Independent Study Team, charged with bringing transparency and scientific rigor to UAP investigations. He also recently served on the National Academy of Sciences Steering Committee for the development of the 2024-2033 Decadal Survey for Solar and Space Physics. Before joining BU, Josh was a senior research engineer at SRI International and worked as a research scientist at the Max Planck Institute for Extraterrestrial Physics. His research is focused on exotic plasma phenomena in the near space environment, using a combination of measurements by ground-based and space-based instrument networks. One particular focus has been microscale plasma processes that require inferential techniques of study. He's an author on over 100 technical papers. He earned a BS in electrical engineering at the University of Massachusetts Amherst and an MS and PhD at Boston University. All questions will be held for the question and answer session after the lecture. With that, Josh, the stage is yours.
All right, it's really great to be here. It's been such an extraordinary visit so far. I loved all the dinner conversations and meeting many of you. This talk was sort of solicited in a way, cajoled possibly. I haven't prepared a talk like this before. If I had to describe my research vision in a nutshell, it's really this James Joyce quote. In the particular is contained the universal. I found early on in my career that, when you point sensors of ever greater resolution ever greater time and space resolution, you see new physics, and it's not incremental. The entire model breaks down sometimes when you look at things at the resolution inherent in the phenomenon. And so that is what I'm going to go after here today is sort of how to apply that modality of research to UAP. And also I'll show you a few pictures of my own work. So this is really where the current bolus in UAP interest began. It began with this New York Times article in 2017, Glowing Aura and Black Money, the Pentagon's Mysterious UFO Program. And to quote the New York Times, footage from Navy FA-18 Super Hornet showing an aircraft surrounded by some kind of glowing aura, traveling at high speed and rotating as it moves. It's interesting to note that it was actually doing none of those things. What the most extraordinary thing about this article to me is that all of the data is in the mid-wave to long-wave infrared. No mention anywhere that we're looking at infrared imagery as opposed to visible light imagery. I'm sure you all know the basic difference, right? Visible imagery, like me looking at you and what's sent in your eyes, is reflected information. These images here are emitting thermal radiation, and that's the picture that you're getting from it. It's absolutely perilous to translate your biases, your experience, your context from visible light imaging into the infrared, and you can have all kinds of fun inventing mysterious UAPs when you do that. There was actually some sobering comments. James Oberg, NASA engineer, was also quoted in this article. There are plenty of prosaic events and human perception traits that can account for these stories. Okay. So what do I do? For those who are interested, I study the electrical and magnetic environment of the Earth. I use high-resolution measurements and physics models to understand exotic natural phenomena wherever I can find it. I build optical sensors in my lab. I enlist high-power, large-aperture radar systems operated by MIT Lincoln Labs and so forth to actually collect weak scatter off the plasma surrounding the Earth. And so I think this was the basis of why I was asked to be on this panel, is I have some basic knowledge of sensors and their limitations and so forth. As an example of where resolution in space and time helps you, I would present to you this object here, which is produced by this process. That's it. And so the idea, of course, is that if you took that photograph and asked for an analysis of it, you'd say, well, that's a really interesting lampshade or something like that. Where in reality, if you break it down into some more detailed information in space and time, you realize that this is a little rotating cylinder with lights on it. Totally different physical information. Plasmas, they're created ephemerally in our atmosphere. And, when we look at them at normal 30 frames per second cameras, we see lightning bolts appear and disappear in fractions of a second. And if you want to know how lightning works, you need at least about 2,500 frames per second, and then you can get the real picture of the process. Okay, so your entire physical model is different. This is a phenomenon related to runaway electrons, whereby you have energy to ionize the atmosphere. That adds more plasma. That gets energized, and you have kind of a cascade effect. And eventually, there's a leader that reaches the ground and completes the circuit. And sprites found their way into our report. It was like page 2 of the report. We had this picture. Sprites are, if you don't know, they're sort of the upward propagating analog to lightning bolts. So they start at the top of the clouds and go up towards the ionosphere. And lots of these high frame rate cameras have been pointed at this phenomenon as well. And here's one at 300 microsecond resolution. The formation of a sprite, it really is quite a fireworks show that happens. And so that image you saw on the previous page was a long time average, long by the perspective of sprites. And then, my favorite topic is the aurora borealis. It's really not all one thing. This is what's happening in this image. You see all these coherent structures sort of like dancing, but they're not really moving once they're created, which is one of the interesting findings I had early on in working on this stuff, is that this is what breaking Alfvén waves look like. Alfvén wave is a magnetohydrodynamic wave that serves as the ducted mode that transfers energy from the deep magnetosphere into the atmosphere and ionosphere, whereby it creates the aurora. And then just like ocean waves breaking, they break into kinetic structures that produce displays like this in the aurora. Okay, so all of that aside, that's sort of the kind of work, the flavor of work I work on. The NASA UAP panel, when I got the call, I guess I've told some of you this when we've been talking casually, when I got the call, I'm like, hell yeah. I mean, I remember when that 2017 article came out, and I had that funny feeling you get when there's some paranormal looking phenomenon going on, and I didn't know anything about artifacts that could appear in infrared and so forth at the time. I was really happy to join the panel. I thought I was going to see a bunch of classified data, in particular radar data scattering off these objects where you get a Doppler shift, and that's a real measure of velocity. All of that stuff. And it turned out everything that was available for me to look at and the panel to look at is the stuff that's available for you to look at as well. It's all in the public domain. And there's apparently classified data that shows something different, but at this point I don't really believe it. Our panel was very diverse in a lot of different vectors. A couple astrophysicists, a science writer, mathematician, 2 people from the FAA. There was defense sector people. We had Scott Kelly, an astronaut. It was great getting to know him. Me, I guess, would be in sort of the space physics category, and so forth. Data scientists. The panel was administered by Evans, who did a great job, and it was chaired by David Spergel. And all right, so we. First of all, this came up over dinner that we've tried to replace the UFO acronym with UAP, and there's a really good reason for doing that. Of course, UFO not only does it F stand for flying, and so it only kind of limits us to that one domain. UFO has become, of course, stigmatized and synonymous with extraterrestrials. And so UAP is unidentified anomalous phenomena. It's meant to cover phenomena that might be in the ocean, in the air, or wherever else in space. And the idea is to remove the stigma. Like I said, the provenance is air, space, ocean, land. And we were granted a charge, and it's really wordy. It's not really expecting you to read all that, but it's really interesting to see that the word data shows up in 6 of the 8 charge items. What types of data, what types of scientific data are collected, archived, what other data should be collected by NASA, what civilian airspace data could help us, how do we manage the large volumes of data, all of these things, but it was all data-centered. Our panel was not a panel of, as you could see by its makeup, it was not a panel of math nerds, data science nerds, or anything like that. It's not like we sat in a back room and looked at data, right? So I think I looked at more data than anyone else on the panel because I was interested, because I was crestfallen. I joined the panel, and all we're going to do is plan for the future. And so the major findings of the panel, let me just go through that briefly. They seem generic, but in the sense they're exactly the right ones. We need better data, okay? We need simultaneous measurements of using different sensors and from different locations, and then we can start talking about whether a phenomenon we observe is extraordinary or whether it's, one of the things we really need to watch out for, and this was a thing discussed vociferously on the panel, is it may not be that we're looking for extraterrestrials or some deep sea living, civilization or something like that. It may be that we're looking for technical surprise. And that I resonate with. I mean, we almost see that sometimes. You look at the latest fighter jets coming out of China and how different they look, and there's a lot of clandestine technologies being developed that we don't know very much about. And that is a problem, and we should pay attention to that. And so technical surprise is a big motivation for collecting these data and having these multidisciplinary and multi-agency approaches in place. So better data is needed, need for a disciplined scientific approach to analyzing these data. So if I fail to do that, I want someone to tell me. This is the thing is, there was a book called something like What I Learned About Business from the Mafia. I can't remember if anybody knows that book. It was 10 or 15 years ago. And I remember the guy saying in his thick Brooklyn accent, as long as you're on the high ground, you got nothing to worry about. And so I'm hoping to stay on the high ground and say, look, this is what the evidence says. I know you have testimony from a bazillion different people who saw something. That's not good. That's not going to work for me. I need some data. The challenge going forward, this is a whole other talk, is that it's very easy to fake data, to fake observations these days. AI is becoming unbelievable, right? At creating any phenomenon that any kind of data set that you want. But that's for another time. So the scientific approach, we should maintain that with rigor. That refers specifically, for most of us, to the scientific method promoted by René Descartes in the 17th century. Chase down a hypothesis, let it live for as long as it can. As soon as an observation contradicts that hypothesis, it's not like you go on and find more information, you throw it out, and you get the one that is consistent with your data and your theoretical model. Need to remove stigma around UAP reporting. So that's a really important one. Also, that's mainly directed at the military aviators. There's a culture of non-reporting of this stuff, and this is also true in the FAA. So this has been kind of addressed there as well. Need for cooperation and transparency among government agencies. This is where things get really dicey, because the true believers, if you will, I don't really know what to call it, the people that sort of don't want to know about all the evidence. The problem you have is that there should be information that's classified, right? I think everybody in this room can agree that the reason for keeping observations classified is not because the target is something we want to protect the citizenry from. It's because the sensor technology is, we don't want the adversaries to know what our capabilities and limitations are. So this is something that's going to get in the way of DoD, NASA collaborations around a topic like this. All right, so we threw Carl Sagan up there. Extraordinary claims require extraordinary evidence. That's just how it is. Okay, so I mentioned infrared, right? We saw those images, and one of the things I want to note is that we have incredibly sensitive infrared cameras. So that thermal signal that you get off of objects, we can discern it. I have a FLIR, a Teledyne FLIR, costs about $380, and this hooks onto your iPhone. I suggest everybody get one. I'm really not working for them. It's just so amazing to take this thing and play little experiments with infrared imagery. Okay, and this thing can detect temperature differentials of 0.02 degrees Celsius. It's phenomenal. And so that's one of the things, is that infrared is very sensitive, but it's also very sensitive to coming into thermal equilibrium with its background. I want to show you a little bit about that. So let's see let's start with auras, right? So we have this idea that there's an aura surrounding an object in the left panel there. So in the left panel, a switch has been thrown on this, what is called AT FLIR, Advanced Tactical FLIR. FLIR stands for forward-looking infrared. And so that's an at FLIR image, and it's been toggled so that the hot thing is dark and the cold thing is bright. That's all that's different between the left and the right. And the right is a FLIR image that we recorded with a system that we borrowed from Teledyne, and we think that's about the same distance away. That's a very small field of view, and something like 8-9 kilometers away from where we had the sensor. And you can see the aura around there as well. And so this is a common video enhancement strategy. Anybody do any videography or photography, you might have come across contrast enhancing algorithms, where you hit it a few times and all of the little creases and stuff come out. It's something you never want to do to your face. But the and so the way you do it is quite simple. Mathematically, it's not that difficult to imagine. You take a neighborhood of pixels and you run it along the whole image. So you create, in fact, a blurry image. Then you take the real image and divide it by the blurry image. All right, and you end up seeing all the little features start to come out, but you get artifacts like this, like dark background. So anyway, that's what this is. Oh, he's lighting up a cigarette, I think here. Yeah, he doesn't know we're looking at him do this. Let's see. There you go. Look, he's lit a cigarette. It's in his mouth, and it looks like a UAP. So that's pretty cool. All right. So the first rule for the world in the infrared is that an aura is an artifact of standard contrast enhancement adjustments. So what else can happen? Okay. Well, I mentioned that we borrowed this system and we set it up on this in Boston. Actually, we set it up on the 17th floor of this audacious building we have, the CDS building. It looks like a giant block of giant Jenga game. It's pretty cool. Anyway, and we looked at the approach path to Logan Airport. The thing about this is it's a combined visible and infrared sensor, and that's exactly what you need to try and figure out what an object is. And so we just had this thing up there. It was a clear day sometimes, but it was mostly overcast. And here's a plane arriving at Logan Airport. On the left image in the circle there, you see a little point, a little dot, and on the right image, maybe it's coming across that you see, yes, you see a nice airplane in the distance, and we can go ahead and sort of track what they look like side by side. So that's a 767 aircraft. That's what it looks like in infrared from this distance. Okay? So that's the other thing, is that you're looking at a sensor that's, of course, highly sensitive to thermal emissions of things like jet engines. And for distant objects, you absolutely wouldn't be able to tell that the size of the actual aircraft you're looking at. I had a lot of people out there in the community kind of attacking the idea, saying, no, the thing we were looking at on the left there is an object that's flying around with no wings and no visible means of propulsion. I'm like, no, that's all you're seeing is the propulsion, I think, for the most part. So let's put that down as a rule. An IR image may not represent the size or shape of the actual object. And that's true. All right, well, do we need any other rules? I don't know. Here's one I put together for y'all. In the upper left is it's a Chipotle's fork, knife, and spoon that are actually physically colored black. They're plastic. They're on my granite countertop at home. And the image on the right is exactly the same. Yes, it's exactly the same. The knife is sitting there in the middle, and you can't see it. And the blackness, so this is meant to kind of tweak your bias. Now, that image on the right looks like the image on the left, except the black in color that you're seeing is actually because they're cold. I cooled them down. And the knife is equilibrated with the background thermally. And so you can't see it at all. And that's the little flare thing I mentioned. So let's see if that's true, that knife is there, or am I just blowing smoke? All right, so this is my little video. And there I go. Okay, the hand's in there. Let's see if there's anything there. He picks it up. And voila, there's a knife. And it looks, now let's just warm it up just ever so slightly. And we'll put it back down. So there you go. Now you can see it. And it holds on to the temperature for a while, but you can see it's starting to bleed it into the background. And so this is what's going to happen with objects that are sort of near the ocean, like birds. They might disappear on you. Okay? I have one other one here that's kind of fun. I put an oven mitt in my driveway on a pretty cold day. I warmed it up, and it's fun to watch and see what it does from here. There it goes. It starts to get eaten away at the bottom. It's turning black ultimately. Why is it turning black? Well, because an oven mitt, its only goal in life is to not conduct thermal. And so it's not reflecting, it's not actually showing me the temperature of the background like the knife was. It's actually equilibrating to the air temperature, which was cold, because that's where most of the exposure is. So the idea here is that we can, let's see, have another maxim for us. An IR image shows differential temperature against background. Objects can disappear and reappear. Okay, and so the last tool you need to understand, the state of UAPs as I see it is the parallax effect. I mean, I'm sure many of you with physics background understand what that is. This is the apparent shift in an object's position based on moving the sensor. Okay, and you can have some, like, you can do this exercise with you right now if you want. You can put your thumb straight up, find a target in the background, move your thumb back and forth, and it looks like it moves. Now put your thumb there again, move your head back and forth. There is absolutely no way to distinguish which was moving. Was your thumb moving or was your sensor moving? Oh, I forgot, you have to close one eye because a camera's a one-eyed sensor. And so if you keep your eyes open, you're cheating because you get stereographic depth perception. Okay, now in that one, that there's one of two things that could be true. Either there's a giant thumb in the back of the room that's moving, right? Or it's closer to me and it's a parallax effect, that the actual head, the sensor's moving, right? And you know the answer because of experience and context, right? In that particular case, as do you. Now this one's a little bit different, but here's another example of parallax, right? There's a innocent star-shaped birthday balloon floating in the sky, and somebody was going by it with a plane, and this is what it looks like when you just sort of track it. And this is exactly the stuff that people have kept saying, there are these orbs going around the planet at high velocity. No, they've been recorded from airplanes and from drones that were moving rapidly, and the thing was floating there. Anyway, I thought that was kind of a fun one to find. I stumbled across that somewhere. Okay, so apparent displacement of an object because of a change in observer's viewpoint, that's parallax. All right, and those four rules are pretty much all I think we need. If we look at, this is one of the cases I talked with a few of you about. This was open for a long time. It's some object that's flying around near the ocean in Puerto Rico, and it disappears there. And people were talking about how it's transmedium, it's going under the water without even splashing. This must be some really advanced technology if you don't splash when you go into the water. And then, and I got a good question for you. How is it that the person tracking knows to keep tracking when it disappears? Probably because he's got visual information also. So that's the thing, is there's a lot of incomplete metadata around these sorts of things. So this is definitely two birds flying around the ocean. That's definitely what it is. I could point you to literally a 26-page treatise on this event that talks about anti-gravity, transmedium, and matter splitting into two and rejoining. I cannot believe how far people extrapolate down that rabbit hole, when they really want to see something. And yeah, I'll come back to that a little later. So this is another event, not this one, but this is forced perspective is one way to look at all this. You can find these all over the place. You can do. I'm sure some of you have done your own creative forced perspective views. And so you absolutely, what do you need to figure out that that's not a giant adjustable wrench on our head, right? What do you need? You need to know range to the target, range to the background. And then it all falls into place. All right, so this was an event that was quite popular in discussion circles. This was recorded by pilots on the USS Theodore Roosevelt in 2015. There's obviously a speck going around down there in the ocean. He's trying to find it. His really sophisticated equipment, and that's not sarcastic, this is really good, at FLIRPod, a Raytheon product that serves as a big part of our national defense. And it can find objects, and through its algorithmic magic, it can lock onto them and track them. And so it's tracking this object. And when I first saw that, I too said to myself, wow, that thing is moving really fast. And a lot of people said that. And not only that, the people in the cockpit said that too. And that's one of the things I would mention, is that you have to forgive the pilots aren't trained for this. The pilots are trained to lock onto that thing and take it out, right? And so it's sort of a different skill set than trying to figure out parallax and so forth. So one of the things you can do with this image is look at all those numbers on the screen. All right, it turns out there is a lot of information on the display that can help you figure out what this object is doing. There's the elevation and the azimuth angle of the camera. So this is the bearing, how far down and how far over is it looking to the object. The target range in nautical miles is given. And there's some unknowns associated with how it's computed, because apparently the radar was off. And all I would say about that is that I don't think they would supply the pilot with the range information if it was absolutely useless. It's got to be a pretty good estimate of the range. It's got the aircraft altitude in feet, it's got a time reference in seconds, and it's got an indicated airspeed. Okay, so you have through those 6 items kind of what you need to come up with a good estimate for that object's distance, altitude, trajectory, and there's some unknowns, right? So you see the tilted line there. For those who aren't familiar, that airplane is actually banking to the left at 15 degrees. Okay, and there's some uncertainty computing true airspeed from the indicated airspeed, because that involves a knowledge of the winds and things like that. But still, we can go through the exercise, and I decided to do it. I'm like, oh, this will be fun, a fun thing to do over coffee on MATLAB. And so what we find here, let's see, we look 35 degrees down in elevation to the object, and the range to the object is 3.8 miles. And so with that little piece of trigonometry, knowing the height, the altitude rather, of the aircraft, that's all we need to figure out that that object is actually halfway between the sensor and the ocean behind it. And it's at 13,000 feet. So absolutely, the conclusion is the object's midway between the aircraft and the stationary background. Parallax is most definitely going to contribute to the apparent motion. What is that motion? Could we figure that out? Now, here's where I can get into a little bit of trouble. Because, like I said, you have to make some assumptions about the trajectory of the aircraft. It's banked 15 degrees. It's an FA-18 Hornet, and you can go to your aerospace references and come up and find an equation for the bank radius at those conditions. And so that's what I used. And what can you do? Well, you can figure out where the object is with respect to the aircraft at the beginning, and then with reference, all you need is you're looking for a delta movement at this point. So with reference to where that aircraft was, you can figure out 22 seconds later I've traveled to here, and same analysis, the object is here, subtract the 2, divide by 22 seconds. And if you do that based on the bank rate model that I used, you get that the object is moving at about 35 to 40 miles per hour. And it may be coincidence, but it turns out that that's about typical wind speed at 13,000 feet, not accounting for the direction or anything like that. From my perspective, so why, I'm doing this because I want to know if there's a technical surprise in this object. I have to say, I think it would be so fascinating if I did that calculation and I found out that it was moving at Mach 5. Seriously, right? I mean, my God, it would be terrific, because whoever has that technology will have it soon and all that kind of stuff. And somehow it's moving without propulsion, all these good things. But no, within boundaries, it's sort of moving at wind speed. We can argue the details, or I'll leave it to someone else to find out. Maybe it's moving as fast as a Cessna. And here I've played around with different bank radii, and you can see its most probable velocity is sort of near 0. And it can be moving either left or right, All right, so the finding is that, considering the plausible wind adjustments, the object's ground speed may be in 0 to 120 miles per hour. No extraordinary means of propulsion is indicated. So here you go, right? Data, let's write it down. What are the 2 hypotheses we're talking about here? Hypothesis 1, the object had a non-zero airspeed maintained by a propulsion system that produced no discernible thermal signature. Hypothesis 2, the object was drifting with the ambient wind, which would be the drifting be consistent with the lack of thermal signatures. So, just based on sort of keep it simple scientists, I'd say that the option is 1, but I also don't know what that object is. Okay? So there's definitely room for further analysis, that's for sure. All right? Let's go outside the IR, the infrared, for a moment, and look at the flashing green triangles. Has anybody ever seen this one? This was exciting for a while. This is a night vision camera looking at stuff, and it's looking at a flashing green triangle going overhead. And it is, let's look at it a little bit more. It's going to come across 2 other green triangles, I think. Oh, there we go. There they are. The other green triangles aren't moving. They are blinking because of the clouds. Does anybody know what's going on here? Yeah, exactly. So, this talk is meant to be sort of accessible to everybody, and I know some of you probably can figure this out really quickly, but this is an issue. It's called the bokeh effect, and we can easily explain it. The circle of confusion is the name given to this. If you put an object, now the line's coming parallel into the lens. How does a lens work, right, for a far field object? Right? All of the rays from any given direction from an object are coming in parallel. You're actually imaging in angle. Okay, so like a point source will approximately hit the lens if it's far enough away. It'll be roughly a bunch of parallel ray paths. And if you look at point B, then you have this perfect focus situation. But there is always a circle of confusion. There's always a region, even for a point source, there's always going to be some spread. No lens is perfect. There's going to be some spread on your focal plane. Does that make sense? Okay. The circle in circle of confusion refers to the shape of the aperture. Right? It doesn't necessarily have to be a circle, but lenses are easy to manufacture as circular devices. And so what happens if you move that focal plane a little bit further back, like in A? Well, you get a larger circle on the focal plane. If you move it forward, you also get a larger spot size. So all you have to do to get a circle to appear, if you're imaging a star, right, that's definitely in the far field, all right, that star is going to show up as a blurry circle if you're out of focus. That's what we're talking about here, right? And it turns out you can increase the depth of field by cutting the aperture down. Somebody mentioned aperture, so that's the idea. If you suppose you make the aperture a different shape, right? And you kick it out of focus a little bit. Then you can come up with a shape that looks very much like the object. So this is crediting Mick West. He's the one who actually figured this out for the government. And it took, like I said, 2 years. This was an open issue for a long time. People can get really fooled by some of these things if they don't work with optics every day. So this one had a kind of a pyramid or whatever, triangular shaped aperture. And so this is actually Capella. This is a star. And so that's what we were looking at. So we talk about within the particular lies of universal, if you find out, wait a second, one of these triangles is a star, that throws the whole theory out. You got to eliminate it and come up with a new idea. Okay. Yeah. And you can get, there's a heart-shaped bokeh you can get. People do this for artistic effect. You can put little shaped apertures on your camera, and you can talk to me if you want to learn more. You need to have the near field object, like the person, in focus, and as long as you keep the depth of field small and the background's out of focus, and you can get things like a person standing in front of a bunch of hearts if you set up a bunch of lights back there, whatever. You can do kind of all kinds of fun stuff. All right. So let me, in the final sort of time here, let's talk about this gimbal one a little bit. This has been widely celebrated. I think Mick West, I mentioned, has spent a lot of time in his recent career trying to figure out what's going on with this object here. So we have an object. We've already talked about the aura. That's not a problem anymore. The fact that it looks structured, is a little troubling to me because it looks like it's saturated. You're right. There's a big black region that's not resolved in any differential thermal emissions, and people like this one, I guess, because it looks like it has a structure to it. It looks like almost like a flying saucer, and here it's rotating, and that's pointed out by the people who are taking this video as being a potentially interesting thing to look at. So you have an object that's flying around the sky and it's suddenly rotating. That's pretty eerie. And so, what might be going on here? What I would like you to check out here is the following hypothesis. Now, you may have already noticed this in your first pass through that little video we just showed, but there are times when the whole camera is bumping, and it just does a bump. And the reason it's doing that is because of the way this mechanics of this camera's pointing work. This is a gimbal mount, okay? So it's got an axis here and a rotation axis. And with those two, I can reach any elevation and azimuth I want. The problem is that there are some points, like if I want to scan this way, and all I can do is go up and down, I can't go this way, so I have to have some combination of rotations and up and down movement to reach all those points. And so there are points, gimbal singularities and things like that, where you actually have to do a rapid rotation to keep that elevation scan going. And that's one thing, that's probably why this was named the gimbal, because we didn't name it that. That came out of the Air Force with that name, as far as I know. So anyway, let's look at that a little bit here and see. Sorry. There we go. What I want to do, here's a question for you that comes to mind. It's like, all right, did the camera bump before it rotated, or did it bump because it rotated? Was the camera trying to track the object that was changing its position, and so it bumps a little bit? Or did that bump happen beforehand? And we can kind of look at that. Look at here. Ready? There's bump, rotate, bump, rotate. I'm betting the bump happens first. So let's take a look at a few frames together. Together we'll debunk this. I don't know. All right. So here we go. This frame 2, frame 3, 4, 5. Whoop. Between 5 and 4. It's definitely, and you'll notice, right? It is the whole field that's bumping. So it's not the object that's moving, right? Look off in the corner, you see that the field actually moves. So the camera is making some adjustment at that point to keep track on this object. And as soon as it does, the thing rotates. Okay? So this is what I should have written this down. So there are two hypotheses here, right? Either that object is responding to the camera adjusting, okay? In which case, it is not an image of the object in the distance. It's an image of an artifact in the camera. If it's rotating with the camera, then it's an image of the artifact in the camera. The other possibility is that the object communicated to my sensor that it was about to rotate, and that didn't happen, right? So then, and again, this is another one that Mick West worked on quite a bit, I think I mentioned. So then it becomes the question of, how can this possibly be? How can you have an object with a structure that looks that way rotate against the background, right? And that is, in fact, what glare does. So if we right, so is one of his videos. Uh, so here's just showing, what is it showing, right? It's showing that the glare of that light is in fact rotating with the camera. All right, but the background is sort of changing because we haven't, like, sort of like the videos that we just saw, the AtFLIR videos, the software that is sort of always registering the horizon in a way that's understandable to the pilot, right? So if the pilot is taking a hard bank to the right, it's going to, on the FLIR, it's going to render the background rotated to be consistent with what the pilot is seeing. So he came up with this clever way of actually using two phones. There you go. So the glare is being produced in the phone he's looking at there, and he's got a camera watching the entire experiment. And this is the sort of thing that we think is happening. And again, it's not predicated particularly on the fact that I don't like things rotating, like an object like that rotating. For me, it's the whole theory that it's an object in the distance with a certain structure. Okay, so first of all, we know that's not true because of our toolbox, our rule book for how to interpret infrared images. All right, we know that structure probably doesn't represent an actual structure of the object, right? And yeah, and so the likely explanation for this thing is that it's a glare function within the instrument, and it's because the camera actually makes an adjustment prior to the rotation that there is either some communication with the object or the rotation is an adjustment due to the gimbal trying to track that aircraft. Okay, well anyway, so those are some examples, popular examples of UAP events. Our report had findings. We also had some recommendations. Okay, adhere strictly to the scientific method. We asked NASA to create a dedicated NASA point of contact, and they actually went and did that. So there is an office and a position at NASA, and we really need to establish baseline data, which is sort of what I've been doing in this talk. And the other thing I want to mention is the role of citizen scientists. And this means all of you. Okay, though, citizen scientists are an excellent resource for unidentified aerial phenomena. Why? Because they're responsive, right? If I have one person showing me a video of the sky and some unusual object and no one else sees it, it's very difficult for me to know anything about it in terms of its position, its movement, whether it's a fake, all that kind of stuff. But on the other hand, if I see something crazy, something exotic in the sky, and I get on social media and say, hey, is anybody else seeing this? Then that is a responsive network for analyzing weird stuff in the sky. It's self-validating because it's really difficult to fake an object from, say, 20 different people viewing it with different smartphones in different locations. And not only that, multiple viewing angles gives you a way to triangulate it and figure out what its altitude is and figure out its velocity. So the UAP research should actually have a huge citizen science component to it. All right. Whoops. Sorry. So I'm all done here. I just want to mention that the whole there's so much wonder in the universe, and it stems from real physics that we can verify experimentally. We don't need to sort of make up explanations to sort of keep things exciting. Mother Nature will do that on its own. Thank you very much.
So we have time for some questions and some answers, hopefully.
Paulo's new member.
Hi.
Great presentation. My question is, the examples that you've shown us, you pretty much debunked them all. But are there any anomalies that, it's Friday night, so that remain X-Files?
Yeah, there actually are. And the data is incomplete. I was just reading one this morning from 1972 about this this UAP that some farmer saw, and it ended up changing the chemistry of the soil somehow so that it became hydrophobic. And it was really detailed, but there were pictures, and I get the feeling it was a real phenomenon. So this is one of the things is that I think a lot of these phenomena can happen due to natural things like methane bubbles and stuff like that. Yeah, I'm trying to think of any that are in the category of this stuff that remain kind of unknown. Avi Loeb at Harvard is sort of has an entire program dedicated to trying to find these sorts of things. I think it's called Gemini. What?
Sorry, he's holding his head.
So, yeah, that's my partial answer.
All right, we'll go to the blue microphone.
Ciprian Ivanov, member. Does the increasing use of digital cameras introduce artifacts that a lot of people wouldn't recognize due to the assumption digital cameras work exactly the same as analog?
Oh, that's a really good question. So we do have to know the artifacts that appear in digital cameras. These glare, mostly it does behave like wet film, but this pixel blooming that can, which is where energy is spread beyond a pixel that's measuring something, and sort of it gives you the impression that there might be a larger object out in space. Along those lines, also digital cameras every digital camera has like a hot pixel or two, and after a while they develop a lot of them, which can be confused with stars and can kind of affect your ability to accurately register the images. And yeah, there's probably others. But I don't think there's anything catastrophic or too serious about the difference between wet film imaging and digital imaging. The advantages far outweigh any disadvantages. Digital imaging can be done at, I showed you 2,600 frames a second. You can get a camera that does literally 200,000 frames a second. You've probably seen these things where you can actually image a grenade blowing up and so forth. I mean, that stuff is just not possible in wet film photography. Yeah.
We'll go to the red microphone.
Mike Albrough, member. Larry, I will ask a question, but permit me to read out a couple of numbers here. The Voyager 1 space...
Whoa, ask a question.
The question is whether your panel really considered the physics implications. We believe in physics, right? Mm-hmm. And the physics is it would take the Voyager 1 spacecraft at 38,000 miles per hour, 76,000 years to reach the nearest star. There may be alien civilizations in the galaxy, but the chance they are with, even when they're 100 years, is minuscule. So the question is, did your panel really promote the physics implications of anything coming from an extrasolar civilization?
Yeah, it's a good question, but it has nothing to do with UAP, in my view. Well, I feel like that people have made that connection because they want it to be there. I can just say anything I've looked at has nothing to do with alien civilizations. And a lot of people try to introduce that to this topic, right? But why should it be synonymous? Like, what's the reason that I always have to come up with some comment about alien civilizations in the topic of UAP? The problems with space travel are well known.
People come here because...
People have to... So the first thing you need to do before you start considering
Conversations
anything practically like that is, right, you need to understand special relativity, general relativity. You need to understand the implications, how space and time disappear when you ride on a photon, and just basic things about how we are in a projection of a higher dimensional kind of phenomenon. And, whether any of this has anything to do with that, I can't really comment, but yeah.
Let's go to the blue microphone. The blue microphone.
Hi, David Rosen, lifetime member. Question, how do you distinguish things like atmospheric phenomenon like mirages, atmospheric turbulence, hot bubbles, and so forth? You didn't really mention any of these atmospheric illusions.
Yeah, that is true. I was focusing on actual technology, you know, and these are actually related to some object that was produced by humans. Our panel did. I think there's a few pictures in our report of some, you know, strange cloud formations if freaked people out, because it doesn't seem like these types of cloud formations should form on their own. You know, this is a famous Mount Etna view, and so the nice thing is that atmospheric phenomena, I think the basic physics around almost everything that we see is reasonably well known. And people will postulate some kind of intelligent connection, but it you know, from what I've experienced, it doesn't live very long as an unknown.
We'll go to the red microphone, then we'll go to the web, and there is somebody with a hand up in the back of the room.
Stephen Reinhardt, member. Given that number one on your list of recommendations was more data, what does a dedicated campaign to get more data look like given the frequency and spatial distribution of these kinds of events? What kind of data collection do you need, and how many of them do you need?
Yeah, that's an interesting question. My response to that is that we shouldn't design dedicated networks of sensors just for this single purpose. What we should do is two things. Maybe build sensor networks that are multi-purposed. We do, for instance, the NexRad radar network across the United States. It's sort of like 78 radar systems that can kind of cover the entire United States in terms of sampling weather patterns. Those are Doppler radars. And so what you could do is, instead of having a large program where you invest lots of money into new hardware, is send lots of money towards software and AI and analysis of the data we have, and see if you can find anomalies. So if I see objects like this and I'm able to say, hey, this happened, somebody's got to measure this, it happened somewhere over Texas, it's very likely that there's historical weather radar data that could find that object and tell me something about its velocity. And in my domain, we build wide field spectral imaging systems that we populate Canada and the United States with. And I did mention this on the panel as well. So this is another piece of evidence that we could use. And it's more about the software data management effort than it is about spending money for new sensors, given that we already have sensor networks in place that could help. So I would advocate a significant investment into multi-purposing sensor networks, in particular optical and radar, that we already have, to try and find anomalies and understand them.
From the web.
We have a question from Preston.
I don't know if your mic's on.
We have a question from Preston from California, who is the former recording secretary for the Society. Are there interesting, elusive scientific phenomena that the panel's recommendations may elicit useful info on, even if we don't get anything useful about extraterrestrial UAP?
Yeah, so that's in fact why we call this stuff anomalous phenomena, because we'll take anything, all right? I mean, it's really fun to see something exotic that has a cause you don't understand. And so there's nothing ruled out in the acronym UAP. That is actually a good thing. That we don't have to say, nope, that's not UAP. You know, anything anomalous, right? This is the most generic acronym anyone could ever come up with. Unidentified anomalous phenomena. It's three words that mean sort of the same thing. And so, yes, especially, you know, I was just describing the repurposing of sensor networks. I mean, you can, this is one of the advantages of AI, is one of the things the AI can do is anomaly detection. So it learns what's normal, and if it sees something that's not normal, it can point it out to you. You know, we talked about that quite a bit on the panel too. We had a couple really good data science professors on the panel.
I'm going to interject a question, which is, so I guess you didn't see classified data, but we do have these satellites up in the space to tell us about whether rockets are being launched towards us. And is there a lot of reports from them about anomalous phenomena that they have to spend a lot of time figuring out? Or they just ignore it all? If
Yeah.
it's not an ICBM headed our way.
Right. Well, okay. So one of the areas it's interesting that you say that, right? We have new geopolitical realities that require for our safety that we're detecting objects coming over the poles, hypersonic objects, right? I mean, ICBMs are not going to be the threat of the future, right? It's going to be lower flying hypersonic missiles that are just almost impossible to detect and eliminate. And so back in the early days of ionospheric research, there are these plasma blobs and structures that appear and drift over the polar cap, and we really had to figure out how to separate those from real targets, because obviously an ionospheric blob of plasma is highly radar reflecting, as is an incoming missile. Yeah, so we have to measure everything all the time. That's an acronym a friend of mine came up with. Measure everything all the time. Mealtime.
So in other words, they do see a lot of things that they didn't know what they were at first.
Oh, well, I don't.
And then they
actually-
figure it
no,
out.
It's classified, and I don't have friends in that area, and they would not tell me anyway. But I don't know if we're ever going to bridge this classified kind of divide in terms of using data from multiple agencies, right? So we have these venerable agencies in the U.S. that are all really good with sensors: the DoD, NASA, National Oceanographic Administration, and Atmospheric Administration, the FAA, right? We could pool data from all these different sources. They all have different perspectives, different priorities, but the big happy family thing is always hard to achieve. Yeah.
I think we are going to the blue microphone.
Hello, thank you for speaking today. In 2023, there was a congressional hearing where there were eyewitness accounts from certain fighter pilots named Ryan Graves and Commander David Favor, who reported seeing with their own eyes a black cube with a sphere in the center of it. I know there's no visual or recorded imagery of this, but what is your opinion of their reports, and do you have a rationale for their eyewitness accounts?
Yeah, so everything that they've described is I haven't heard anything that they've described that sounds like it couldn't be accounted for. So, for instance, a sphere with a cube in the middle, that's a radar reflector. I'm sure there's lots and lots of those floating around. You can actually go on Amazon and buy one of those. You fill it with helium. It's got a radar reflector in the middle. You use it if you're lost at sea. It's just a standard device. So something like that, that makes perfect sense now. Alex Dietrich, the Tic Tac thing, they saw something, no doubt. I don't know what it is. I don't, and I'd love to know. I think they would too. So it was her and David Fravor that saw the famous Tic Tac, and they've sketched it out, and through the years have tried to understand what that was that they saw, and it seems like that topic's at an impasse. All I would say is that if there's data, then count me in. That's the thing. Testimonies, I don't really have a comment about it, except that yes, you saw something, and we should try to figure out what it was, if that helps.
Red microphone.
Aki Raberge, member. I was wondering if you could say anything about what the effect of this study has been on what you might call enthusiasts. If you can say that the thing you're looking at is not the thing you thought it was, but you can't tell them what it is, does that make any impact?
Well, I don't want to speak in generalities because I think everybody is different. And I don't know if I could identify a general group of people that would all respond in some one particular way. In general, there are definitely people who sort of can't be convinced the other way around. There's a really good Scientific American article by the former head of the All Anomalies Resolution Office, Sean Kirkpatrick. And he actually resigned in protest from the office because there were, at the highest levels of government, people that kind of would not let their thinking change, even though contradictory evidence is presented. And I don't know what that phenomena is. I'm interested in it, how people I mean, Kahneman and Tversky talk about this stuff in their behavioral economics, treatise and everything. That once you lock into a certain bias, your body viscerally prevents a change because it's really uncomfortable to be wrong. But on the other hand, I come back to what I said at the beginning. I treat every person individually, and I get lots of emails to try and answer. And when someone goes down a road of extrapolating, with these events, we don't really know what they are, right? And when you then extrapolate that into something truly extraordinary with a big story behind it, that's fine. That's a hypothesis. We should test it. But I don't know how. And I don't know where we get the data to find out if there is underwater civilizations that have been developing thousands of years before humans, and those sorts of things.
Occam's razor.
Occam's razor. Yeah,
it's very useful. All right, that was red, so now we're at blue. Blue, we have blue microphone here.
Hi, Matt Kaywood, member. In 1917, Arthur Conan Doyle, who was a great, if we think of as a skeptic, author of Sherlock Holmes, was completely blindsided and fooled by these girls who had these fairy pictures that they cut out of, magazines and took these photos with, right? Cutting them fairly, I think is the name. That was sort of the birth of photography. And it seems like one of the things you're talking about is that we're really early in the stage of, sort of infrared, and even people, folks with military training who should know some of the limitations of IR and night vision and so on are still being, wildly fooled by the sort of, nature of IR photography. How much of the problem is this? And is that something you think we could fix by just, putting more IR cameras on iPhones?
I would say that, I can only speak from my perspective, and I may be just not the right person to talk to because I'm just fascinated by how sensors work and what kind of projection of reality they give you. And if everybody could just get a baseline, I think that was one of the recommendations of just get a baseline for how to think about IR imagery and really understand that it's giving you a different projection of reality. And in fact, it's not to say that should be visual imagery because that's the only thing that's worthwhile. The combination of the two is unbelievably valuable. And so I'd like to think that everybody's fascinated with learning how the sensors work, whether they're audio sensors, visual imagery, infrared imagery, electromagnetic, that's how we measure the world. And and if you're not interested in it, that's fine too. And I start with the premise that everybody wants to know how their camera works.
Do we have a question from the web or is... No. Okay. So which microphone are we up to? Red microphone. Thank you.
I was just curious if the
name.
Oh, Ben Bradshaw. I'm not a member. Just curious if the number of UAPs over time has gone up with the number of cameras and sensors, or if there have been unexpected negative correlations.
Yeah, there's a slide I didn't include here which shows some stuff from that Aero office I mentioned. That's basically the distribution of UAP reporting across the globe. And not surprisingly, it's off the Atlantic coast, the mid-Atlantic coast, where all the military bases are, and it's off San Diego, and it's in the Japanese area, and so there's a real selection bias. But what is it? To me, that's also information, right? Let's go back to the aliens. I mean, are they somehow able to find all the military areas? No. These are Chinese spy balloons and things like that, very likely. But I also come back to technical surprise, meaning that I actually think there's a reasonably good chance that somebody in this world with their billions of dollars has actually gotten some kind of breakthrough in propulsion technology. And I just wouldn't be surprised if that's sitting around somewhere. It's not going to be anti-gravity or wormholes or anything like that. I mean, it's going to adhere to the second law of thermodynamics. I'm sure of that. But I think that there's quite a possibility that we'll see something extraordinary in that developmental area.
Why do you think people are so eager to look at something that they can't explain and explain it in a very far out way? Oh, there's some thing that looks like a green triangle. It must be aliens from another planet.
Yeah.
Why do you think people are so eager to have that explanation?
Because it's easy to make money keeping things in the spooky category. I mean, there's characters like Jeremy Corbell who that's what they do. They're not even being nefarious about it. They're just like, this is my livelihood. And that green triangle thing was denied by these people for the longest period of time. It is absolutely, without a doubt, the bokeh effect. That's what's going on. It's a triangular aperture.
It's not those guys. I understand they want to make money and make themselves famous or something. It's all the people who follow them. And the Pied Piper has to have the children who are going to.
But yeah, all economies have leaders and followers.
It's kind of weird to me. Like you immediately decide it's little green men from another planet and they're hiding or they live under the ocean.
Yeah.
Because you saw something you didn't quite understand in the window. Anyway, if there are no more questions, then we will thank our speaker.
Thanks. Thank you.
Thank you. And,
Thanks for having me.
we have our gifts for you. One is a framed copy of the announcement of your talk,
Nice.
signed by all the members of the General Committee on behalf of the membership. We have a ribbon, which is our PSW ribbon. It has 3 bars on the side, evocative of the symbol for inductance, because our founder was Joseph Henry, and he studied inductance, and the unit of inductance is called the Henry. And we have a copy of volume 17 of the PSW Science Bulletin, actually known as the Bulletin of the Philosophical Society of Washington, which contains a lot of the important material from volume 1 and a paper by someone whose name escaped me, Professor Rothenberg on PSW's early history, among other things. A list of our Henry speakers and several histories of PSW, and makes for good airplane reading.
Yeah.
So with that, let me thank you again.
Thanks.
And before you go, we have a few housekeeping announcements.
Oh, okay.
Before you, the audience, go. Our next talk will be the 2514th meeting of the Society on April 25th, 2 weeks from today. It will be at 8 p.m. here in the Powell Auditorium for the lecture. The speaker will be Jamie Bach, Professor of Physics at Caltech and at the Calvi Institute, and also Senior Research Scientist at JPL. He'll be speaking about the SphereX mission to survey the universe in the near infrared and probe the epoch of reionization and expansion. Embarrassingly, the 2516th meeting has not yet been scheduled, but we are working on it. And that may occasion a rescheduling of the date of the Henry. But we will be having the Henry. The 2516th meeting will be on May 30th, and the speaker will be Mark Palmer. He's the chair of Accelerator Science and Technology Development in the Technologies Directorate at Brookhaven National Laboratory, and he'll be speaking about muon colliders, which don't exist, but they're a really interesting idea with interesting physics and technically very challenging. So I thought it would be interesting and fun to hear a talk on how they're going to actually create an instrument that can do the sort of things you need to do in order to have a muon collider. The 2517th meeting will be on June 13th, and the speaker will be Alex Creeley. He's the director of tokamak operations at Commonwealth Fusion Systems, which they're building right here in Virginia. And he's going to talk about what they believe they're going to actually achieve, which is the production of commercial scale electricity using fusion power. The 2518th meeting and the last regular Open lecture meeting of the spring series will be on June 27th. The speaker will be Jason Dworkin, senior scientist for astrobiology and project scientist for the OSIRIS-REx mission, a mission very fond to me because I saw the launch on a perfect day with a perfect launch. And so I'm very excited that he's going to come and talk. Of course, the mission was very successful and brought a large amount of the asteroid Bennu back to Earth. And he's been studying it out at NASA and has very interesting results he published recently. And he may be able to tell us some more things when he speaks on June 27th. And the 2,519th meeting will be an annual meeting of the Society, and that will be for members only, where we talk about the state of the Society, and people get to ask me questions and put me on the hot seat. And so with that, I will thank our crew. Thank you guys for doing the cameras and all the rest of it. And with that, I'll accept a motion to adjourn the meeting. On a second? A third? No. All in favor? All opposed? The meeting is adjourned.